the modulus of the closed bracket AB
Yes.
is equals to B minus A is greater than 0. And then he says, where the first inequality about holds because outer measure preserves order. And the equality comes from 2.4, which is another equation for Heine-Barrow. And then because every countable subset of R has an outer measure 0, we can conclude that I is uncountable.
Correct. Exactly so. So that's what I was saying. Every singleton is measurable and its outer measure is 0. But we have intervals, so the outer measure of the real line is greater than any interval, but it is not 0. Greater than the length of an interval, but it is not 0, and hence it must be uncountable. Yeah, that's right. Correct.
Yeah.
Now, as I said earlier, we bring in, so measures is another structure. If you remember, a measure is a function, positive real valued function defined on measurable subsets, and it has certain properties. Okay, so it is another structure imposed on the set of real numbers, right? And the whole intention, as I said earlier, of putting these structures is to make it simpler and easier to understand the properties of the set. So the structure of measures make it simple, even more simpler, but you see, although you see it in one line, it is not true that it is a one-line proof, because of the fact that if you have to construct that measure, that outer measure, that is where the main muscle is being hidden. Okay, so here when you don't have anything, you are using your muscle to exhibit the absence of surjection or the absence of a bijection or so on. But there you are using the muscle to create another structure, and that structure immediately says. So it is, how do I say, it is actually, it is not true that the proof is one line. The proof is one, the full sentence should be the proof is becomes much more simple given the information or construction of a outer measure. And once that becomes known, then the rest is simple. Yes, that's true. So that's always the case. Sometimes we get hold of structures, as I said before, the whole issue of bringing in structures is to make it possible to understand the properties of a set, the properties of subsets of a set and so on, much more clearly than we could have done just by analyzing the formula which defines the members of the set. Because a set is just given by a formula. Anything satisfying that formula is an element. Now, if we just take this definition, then it becomes almost difficult to realize what are the further properties of that. Yeah? Possibly this answers your question. So yeah, that becomes much more simple. But yeah, that's where I will stop with this. Yeah. Does it make it clear?
Yes, it does. Thanks.
Okay. Now, Charles, you were saying something. So, what should we do today, and what were you saying?
Yeah, I was failing to distinguish between a partial order and a partially ordered set.
Ah, I don't know.
Is there a distinction between them?
Yes. It is just like saying. Well, a left-handed person and Garner is left-handed, just like that. So left-handed person is someone who has an affinity to use his left hand much more often than his right hand, his or her right hand. And when you say that the bowler Garner is left-handed, well, you are saying that he has that property. So a partial order is a specific that can be defined on any. So I'm trying to share my screen. So a partial order is a special kind of a relation. Well, obviously, on a set is a relation, is a, can you see my screen?
Yes, Doc.
Yes, we can, Doc.
Is a reflexive.
Don't forget to record.
No, I'm recording. Transitive and antisymmetric. Okay? Relation, say a relation which we usually denote by this. Okay? And then when we take this set X plus its partial order, so this pair is often called a partially ordered set. For instance, this set X could have different structures also. For instance, let's take the set of real numbers. So this is the set of real numbers, but when we consider the ordering of the real number, we say that R is a partially ordered set with its usual order. Okay? Or here is another partial order which is usually called on R cross R. For instance, we say this is usually called the dictionary order. XY is less than or equal to X prime Y prime. What does this mean? This means either X is less than or equal to X prime, or X is equal to X prime and Y is less than or equal to Y prime. So this is usually called the dictionary order or the lexicographic order. Think how you search your dictionary. You are searching for the word patent, so you carry on from A, B, C until you go to P, and then you go to PA, PAL, PAL, you still go after that, PAL, T, paltry, and so on, and then once you come to PAT, then you start looking, right? So that's exactly the thing that we are doing. So how does this order look like? So if you have this as your real in the plane, so if you take a point xy over here, then everything whose x coordinate is bigger, so let me put it here. So everything whose x coordinate is bigger than x, all of this thing, the moment x coordinate is bigger, it is bigger. All these points are bigger. And if this was the case, if you take the x coordinate in the y coordinate, so this denotes all the elements which are bigger than. So x prime, y prime, which are all bigger than xy in this description. Yeah. Now, when you take, well, R cross R has several other, R cross R is a vector space, R cross R has an addition. If you add coordinate wise, under addition it is a group and blah 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 and so on. But when you consider R cross R with this order, you say the lexicographically ordered plane, or you say this is a partially ordered set. So that's why I said Gardner is a left-handed man. And being left-handed is a property. But when someone is attributed with that property, it means that person has that property similarly. Is it clear now?
Yeah, indeed it is. I was also
one more thing. Sometimes it might still happen that the same set may have several partial orders. Same set may have several partial order relations. Several. So let me give an example. Let's take the case of reals. Okay? One partial order is the usual one. Another which I write as its op. So, x, if and only if x is actually bigger than. So in this order, and then I can have another partial order. Let me write it at this. How do I write this? Well, this is I say that let's say that x is this prime if and only if both x and y are rational numbers and x is less than or equal to y. So I actually twist things. So let me say if both of them are of the same kind, so if x and y are both in this, or x and y are both not in this, then else, that means if one is a rational and the other is an irrational, I just reverse the order. So you see, R makes three partially ordered sets. This is one partially ordered set. this is another partially ordered set, and this is another partially ordered set. Why? Over here 0 is less than 1, over here 0 is not less than 1. Over here, as you can see, 1 is less than 0. Yeah, is the opposite. Okay? And over here, but here 0 is less than E, here E is less than 0, but here 0 is less than E and 0 is less than 1. No, here it's the other way around, sorry. So E is smaller than 0. Okay? So you see, different things have different answers depending on the partially ordered set that you take. Yeah? So here is another example. If you take n, 1 is the usual, this means that there exists a P such that n is m plus p, which is the usual order. And here is another order. So I am writing down the order now. 0, 2, so I am saying 0 is less than 2 is less, so I am saying less than, so this is another order. And after the end of all the even numbers, I put in 1, 3, 5, and so on. Right? Now here you see, with the usual partial order, every subset has a smallest element. But here, with this partial order, this is not true. For instance, the odd numbers, let's say, how do I, every subset has a smallest element. How do I do this? Let me I'm trying to bring in the set. Okay, the set how do I do that? Or yeah, the set of say numbers n in n such that here there will be a, I want to make no, over here it's another no, not this property, another property I was trying to think. I was trying to think of another property which doesn't hold for the usual naturals, but it holds for this one. This one holds everywhere. This one holds everywhere. I'm trying to think of a property.
Can we think of a mapping somehow? I was thinking of the mapping between the naturals and maybe the reals.
Yeah, you're right. I'm exactly trying to think of it in that way. Okay. Okay. Okay, I'll come up with a property. Let me think a little more. These two partially ordered sets are not of the same type. Okay, so they are not. So what do you mean by they are not of the same type? So by saying so, what do I mean that they are not of the same type? Essentially, it means that a property which will hold for one will not hold for the other. So that's exactly where this order preserving maps come into the picture. So if you have two partially ordered sets, for the time being I am still writing this as this, but very soon I'll just use only one symbol. Okay, so a function, so by this we mean that f is a function such that for x and x prime in x is smaller than x prime implies that their images are also smaller. Satisfied. So the f over this is this. That means f, the function f, is very special in the sense that it preserves the partial order, the order relation. Right? Now, in this case, when you have, if you have two such partially ordered order preserving maps such that f composed g is identity of x and g composed f is identity of y. So which means as functions f and g are bijections and g is the inverse of f. So what does this mean? This means that not only are the elements of x, so bijection meant that these elements were just given another label, right? So as sets, this is the same story. How 1, 2, 3, 4, 5, 6. But it also means something, that if this element corresponds to this element and this is smaller than that, then the image, so it's something like this. So by this I am saying this is smaller. So you can see the picture is the same. So in this sense, both x and y are actually the same partially ordered sets, and we call them to be isomorphic. For sets, remember we called it to be bijective. Here the word morphic comes into being from the word morphism, which means shape. This means shape. It's a Latin word. And iso means similar or same. So isomorphic means they have the same shape. So that's why the moment we know that they have the same shape, we know they are. So even if, for instance, this n and this n, they are not isomorphic, although I know as sets they are the same. They are in bijective correspondence, obviously. But as ordered sets, they are not the same. Okay? As ordered sets, they are not the same. So, then I'll give you a property as ordered sets. Are different. That means there is no isomorphism. So you see how what we was bijection for sets now gets translated to the notion of an isomorphism here. But see one thing, this equation, this was still true. Bijection means both of this happened, but they were just set functions. Here they are not only set functions, they are set functions plus this extra property. Amidst such functions, we are searching to find isomorphism, finding this equation. And the word homomorphism will be used. So such things are often called homomorphisms, or morphisms or homomorphisms. The word homo means similar. This means similar. Similar or so of the same type, of the same kind. So that's when we speak about homomorphism. Yeah. So that is one thing one must keep in mind immediately, that there can be several structures, but we will think of, when we speak of a partially ordered set, that means we have selected from those several structures one particular partial order relation on that set. Okay? Yeah? Is it clear?
Yeah, yes, Doc, it's clear. Yeah. But do we use the words partial order and pre-order interchangeably?
No.
No.
Pre-order just doesn't have this. If you don't have this, so that is reflexive and transitive, that is called a pre-order. Now, let's see, we saw this actually. We saw this. Remember, when we tried to compare injections or surjections, so remember what was the comparison. Let's take injection. We have a set X and an injection we said that M is less than or equal to N to mean the existence of P such that M is equal to NP. Yeah? And remember, we showed that M we showed it is reflexive. That means this always happens. When M and N are same, you take P to be the identity. It is you just compose these maps, okay? But it was not antisymmetric. Why? M less than or equal to N less than or equal to M. This happened if and only if there exists a P and this P was a bijection such that M is NP. So M is not equal to N in any way. So there was this bijection in that case. So in that particular case, we had this picture. We had this P going in on one side to make M smaller than N, and we had its inverse making N smaller than. So they are not the same. And then what we said that, well, we will say that M is equivalent to N in such cases, right? Remember we did this. And then we did another trick. And what was it? We considered the equivalence classes. Okay? So we said this to mean that M is less than or equal to N and less than or equal to M. And then we said that if M prime is equivalent to M less than or equal to N, which is equivalent to N prime, then M prime is also less than or equal to N. So using this, we therefore said that the equivalence class, remember our equivalence class, was said to be smaller if this is if. So we defined this relation, and this turned out to be a partial order. So actually this one is a pre-order and this one turned out on a separate set, remember. This one turned out to be a partial order. And in fact, this trick is generic. And that's one of the first things that I did in that, I believe, where is it? That's possibly one of the first tricks that I did in Theorem 9.5. So what did I do? So suppose suppose this is a pre-ordered set. So this means this is a reflexive and transitive, not symmetric, not antisymmetric. So we define X is equivalent to Y if and only if X is less than or equal to Y and less. So see, now we just did, instead of, so we have just taken this. Okay? And then, just as we did before, clearly, X prime is equivalent to X less than or equal to Y equivalent to Y prime implies that X prime is less than or equal to Y prime. This is an equivalence relation on X. So we have the factor set. On this factor set, we are defining this relation. What is it? X by this is less than or equal to y by this. This to mean x is less than or equal to y. So that means I have defined, actually speaking very formally, this is the set of all these ordered pairs. Such that x is less than or equal to y. And now this one actually says that even if I took x prime to be the representative, so in this case, even if I took instead x prime by the equivalence class of x prime, since the equivalence class of x prime and x are same, the same would have been the answer. Okay? Same would have been my conclusion. And now it turns out that this is a partial order. That means this turns out to be reflexive, transitive, and antisymmetric. Antisymmetric precisely because of its definition over here. Okay? And this gives rise to this beautiful. So if you take the factor map, remember this was the factor map, taking each to its equivalence class. Factor map. So now we have so here if x is less than or equal to y, this means this is obviously less than or equal to this, right? And this is nothing else but your image of this. This is nothing else your image of this. So this is order preserving, and not only is this order preserving nice map, but you have another thing. Suppose if you take, let me write this in another color to say that this is a partial ordered set. So suppose if you take another partially ordered set and you take an order preserving map, then you can find a unique order preserving map. And what will this do? Well, that has only one way to do it. Just think a little bit. This has to take it to f of x. And the fact that the way we have defined it says that this is a good. So if you did take this, replaced this by x prime of this, if this was same, so this meant that x is less than or equal to x prime is less than or equal to x. Now, since f is order preserving, this says fx is less than or equal to fx prime less than or equal to fx. But this is a partially ordered set now. So, this says that fx is equal to fxy. So this still goes to fx prime by your formula, and these two are same. So this is well-defined function, and this is order preserving. So this is the unique such function which makes this diagram to commute. So in a sense, you can see that the the construction that we did before while comparing injections and surjections is very generic, and it holds for every preordered set. From every preordered set, you can get hold of the best partially ordered set representation of that. So, and that is by taking its factor. That is the essence of 9.5. I think, I don't know whether you came up to this point or whether, but this automatically comes in. I couldn't stop because the flow is so natural after you ask that question. See, we actually did this. We did pre-orders and partial orders, but we never mentioned it. I hid those names earlier.
Yeah, it's quite a good thing that now I'm beginning to understand even the previous one. Now trying to link the two between them. Yeah, it's okay now, Doc.
Okay.
Yeah, I'm now understanding this comparing of surjections and also the injections now makes sense. Thank you very much.
Next. Next question.
I think we can continue on these partial ones in the absence of, because the other thing I wanted to ask, but then it's a bit different from this, so I didn't want to disturb the flow of this. I was just going to ask it after.
Yes, please ask.
It was just a question which I came across on the last year's paper, which was about the bijection between a bijection on a Cartesian product of two sets with singletons.
What was the question?
The question was just simply saying exhibit a bijection between S and B multiplied by a singleton, which is 0, union A multiplied by a singleton 1.
S and
so
B.
S is defined as the set which is equal to A multiplied by a singleton, which is 0, union B multiplied by 1 as a singleton again. And then they wanted us to check whether that one is a bijection. But that's why I'm saying I'm failing to frame it properly.
Yeah, this one, right? S is this.
Yeah, something like that. Yes.
Okay,
exactly.
and then
they just want us to check whether it is a bijection.
Bijection from between which two sets?
Between S and B. Sorry, the order is changed there. Between S and B times 1 union A times 0.
Okay, even if you put this, as you know, union is commutative, so this doesn't matter. But since it is equal, no, I think it is which year's question?
It was last year's question, 2020 February. Because the first one they say, show that there's an injective. So show that there exist injective functions, A mapped to S and B mapped to S. That was the first equation.
2019.
2020.
Yeah.
So they wanted us to check first whether it is an injection for that one. A A being mapped to S and then B mapped to S again. Or maybe I'll ask it in the next lesson, maybe.
It's question 3.
Yeah, question number 3, I think so.
Yeah, you have to show that there is an injection from here and here, right? You have to produce 2 injections, right? I call this iota 0 and iota 1 if I am not wrong. I see the question in front of me.
Oh, you get it?
Hmm?
Yeah. Because the font which they use there for me is a bit small. I can't.
Yeah, yeah. So, you see, what are the elements? Remember, this is nothing else but what we understood as the disjoint union of A and B. So, what are the members of S? They look like this: X, Y, where Y can only take the values 0 and 1, and if Y is 0, then X comes from A, and Y is 1, then X comes from B, right? That's exactly the meaning of this, right?
Or some kind of indicator function, like.
Kind of, yes. So this X, obviously X over here goes to X0, and Y from here goes to Y1.
Okay, yeah, I get it now.
And those are the injections. This is exactly the coproduct business that we did before. Given any set this and so on, you show that this is there exists a unique function. Remember this we did while we were doing coproducts.
Yeah, you are right. But I was failing to structure it like that.
Yeah, it was not structured like that. But this year I put it in that form. So this S is nothing else but what we said as our A plus B, if you remember.
Yeah, I remember this one, yes.
Yeah.
So now turns up into a commutative diagram now.
Yes. All that. Yes.
Yeah, no, thank you very much.
Okay.
I'll take it from there, then I'll post it to you.
Okay, sure.
Yes.
Any further questions?
Yeah, for now.
I'm fine, Doc. Thanks.
Thank you. Hopefully, Ayub will return next time, and then we will continue with this.